Okay, well, thank you so much for giving me the opportunity to talk about this. It's a bit of quite a challenging task. First thing I want to get an idea, how many here of the students have taken a course in general relativity? Would you raise your hand? Does that mean that all the students have taken general relativity? Or there are a few that haven't? There are a few that haven't and are shy and don't want to say, don't want to get in the spot. Okay, so 85 or 90% of the room are going to hate me for this because I'm going to be talking about things that you really know probably better than I do. But hopefully this is going to help those few of you that haven't had the chance to take a class in general relativity and don't promise you're going to learn general relativity from, a couple hours of lecturing, but at least it's going to introduce you to the jargon and a little bit of the ideas that we're going to need to go into the true topic of this part of the workshop, which is gravitational waves, how are gravitational waves produced, how we understand them in the context of Einstein's equations of general relativity. And to do that, we're going to have to talk about the weak field limit, and it's a crucial concept. And I wouldn't be able to talk about the weak field limit without using all the jargon of general relativity. After that, hopefully, I can talk about sources, a little bit of the history of gravitational waves, and one of the things that is particularly interesting is many of you probably don't know this, but the history of gravitational waves in its early stages is related to the history of physics in Brazil and in Argentina. There was a mentor and educator of, probably many of them are already retired. A whole generation of theoretical physicists in Brazil and Argentina was Guido Beck, an Austrian physicist who emigrated when the Nazis came to power in Austria and Germany. He founded the theoretical school of physics in Argentina and in Brazil as well. And he is the person who found the first exact solutions of gravitational waves in the weak field limit that Einstein didn't understand until, 15 years later after Guido Beck. So there's a relationship of gravitational waves with Brazil and Argentina, which hopefully I'm going to be explaining at some point later in this week. So let me tell you what the plan for this 5 lectures is. My plan is to go over a review that, as I said, it's probably going to be a bit boring for many on special and general relativity, especially very quickly on general relativity, and then introduce the weak field limit, how gravitational waves are produced, and then a little bit of the history and the sources of gravitational waves that we're going to be searching for. And so, going very quickly through all this material, there is an implicit concept in Newtonian mechanics, this idea of absolute time. And with Galilean transformations, we don't talk about an absolute system of reference now. An absolute system of reference. But it's not an absolute system of reference, but several of them. But within this concept, we're still using the idea of an absolute time. And, you all seen and study even in elementary physics, Galilean transformations, and they show how you can go from one inertial system of reference to the other inertial system of reference that has a relative speed between them given by Vx, Vy, and Vz. And we all know the two possible descriptions for an observer that is moving respect to a different one that's seeing a free-falling object as a straight line. It's going to see the parabola because it has the horizontal component added to his or her picture. So special relativity, this is not true anymore. And so with the Galileo and with Newton, we know that Newton's laws are invariant under Galilean transformations. But now, if we want to include all laws of physics, for example, Maxwell equations, this would be true using just Galilean transformations. So Einstein formulated the special theory of relativity with two very basic and simple postulates. All inertial observers are equivalent. But the second crucial one is that the velocity of light is the same in all inertial systems of reference. And obviously, this statement is not immediate. And it took a long time to figure out how to incorporate this into basic principle of physics. And the idea is that you want to do Galilean transformations, and you have a flashlight and a gun, you shoot a bullet, you turn on the light, and it's not going to work the same way for the light as it works for the bullet. And an interesting fact is, you're learning in all books that Einstein used Michelson's experiment. Actually, there's a very interesting book. If you haven't read it, I strongly recommend reading it. It's written by Abraham Pace, and it's called Subtle is the Law, which is the scientific history of Einstein thought. And I had to teach my school general relativity and gravitational on a regular basis. This is a semester-long class, and I always encourage my students to go and take a look at that book because it's quite interesting to see the genesis of Einstein, how he achieved his idea, how long it took, and at the same time to appreciate his genius. So he really and upward motion of celestial objects about their true positions depending on the velocity of the observer. So the aberration causes the objects to appear to be displaced towards the direction of motion of the observer compared to when the observer is stationary. So this phenomenon wouldn't happen if the speed of light was the same regardless of the system of reference where you're observing light from. And the other one, which is quite interesting, if you ever had the chance, it would be very, very cool to go through the entire experiment, Fizeau's experiment. Fizeau's experiment consisted, it was actually 19th century, in the middle of 19th century, it's measured the relative speeds of light in moving water. So moving in the direction of water in motion in a tube, and measure the speed of light against the motion. And actually, his experiment was so precise that if you use Lorentz transformations, you can calculate the differences. And so he got the difference, right? But that difference were eventually explained using two experiments that actually used Einstein to develop the theory of special relativity. So going quickly over Lorentz transformation, I'm pretty sure that even those who haven't taken it, you've been exposed to that. So you had the system of reference, O prime. One is, has a relative velocity v respect to the other, and we label the coordinate with the prime on the moving. I get the feeling that this is still working. It's working? I don't know. Oh, yeah. And and I'm not going to spend much time on this. This is Lorentz transformations applied to one system to relate it to the other. The most important thing that I want to emphasize here is that this quantity is the same in both systems. So this important invariant quantity, we're going to carry it over as we move into developing a general theory of relativity. It's called an interval, and the mathematical significance is at the core of the geometric structure of space-time. This defines a space-time in which the time has an equal footing with the space coordinates, and it gives a totally different structure from the one that we are so used to in this particular scenario is a Minkowski space-time. We're going to see that we're going to need to generalize these space-times to a larger class. So this is between transformation and the Lorentz transformations. And so while in the Galilean transformations, work with differential. In a particular case, it gives a structure that is a Minkowski space-time. Going over very quickly over the Lorentz transformations, we can think about imaginary times, so that way we get the minus, or we can think now, and this is in terms, that while the structure of Euclidean space is invariant, so we have now a different geometry where hyperbolic transformations remain. So under hyperbolic transformation, the Minkowski remains invariant. Solely for the prime coordinates, what we would see is similar formula. See, we take minus v for the prime. And, well, Lorentz form a group with mathematical groups. And this quantity, as they said, is an invariant. Of course, I only notice it now. It's lacking the differential of t squared here. And now, let's look at how velocity, if we take it one step further, velocity will be time derivatives of the positions, and then we take one more time derivative, we're going to get time derivatives. The velocities are going to be acceleration. I want to look at one particular result of the concept of acceleration in the context of the special theory of relativity. And with that, we're going to move on to general relativity. Obviously, the velocity of a third object now. So an object is described from a prime and an unprime system of reference, and how two different observers are going to calculate that velocity. So we had to use factor is this factor. And so just doing the calculation indicated here, prime respect to t prime, we're going to get the prime velocities. And those are going to be related to the unprime velocities. And And now we want to go one step further and take the accelerations. And one thing that we're going to assume is that the accelerations can be expressed in this way. Other accelerations, the unprime ones, through particular metrics. This metric determinant that is actually we can define taken in the unprimed system of reference of the velocities in the unprimed. And vice versa, it's going to have a so there's a one-to-one relationship between the two accelerations. So is one system of reference, it's going to remain zero in the other system of reference. But what happens is they're different from zero. When they're different from zero, the accelerations are going to be different. And so we get that while in general, in Newtonian theory, position, velocity, relatives, and time and acceleration are absolute. In special relativity, acceleration still remains absolute, but we're going to see that in general relativity, everything relative. And so we can now of uniform acceleration and trying to respect Newton's law. So we know that body that has an acceleration in a uniform acceleration, of course, it's going to have an acceleration that's constant. Now, if we have in special relativity about an acceleration, that doesn't mean that eventually it's going to increase the velocity limit and relativity. So, due to this fact, plot made in, I think I did it in MATLAB. I don't remember now what I did it in. But essentially, we have that the acceleration is 4 in the case of the green plot, and the other one is 5. And we see the asymptotic limits for both accelerations. What is interesting is that this line defines event horizons. So these are when speed, that is speed of light. You can't go beyond that. And in that sense, they're trapping surfaces. And nothing is going to appear there because the particle is moving in an accelerated way. And actually, if you look at this, Hawking said that actually in these event horizons you can get a type of Hawking radiation effect. And in principle, this makes it very difficult to have an absolute definition of what are elementary particles. But I'm not going to talk more about this. I just want to mention the fact that the constant of acceleration now has a complete different meaning as compared to the absolute accelerations in the Newtonian worldview. So to go to the general theory of relativity then, there are two ingredients that are key. First, we need to include gravitation. And second, and Einstein characterized a particular thought, which is in this idea, as the happiest thought of his life. It's the idea that a person in free fall with a given acceleration doesn't have any way of distinguishing if it's just in free fall due to the gravitational field, or it's been accelerated because he has its frame, the frame that the person is attached to, some uniform acceleration. And this is, it's called the equivalence principle. The equivalence is the gravitational force acting on the body to the acceleration experimented by a body attached to frame. Well, too many experiments, sorry. A frame that has the same concept. So he said, is it conceivable, this is Einstein quote, that the principle of relativity also holds for systems that are accelerated relative to each other? And one of the most important results that he worked before developing the whole general theory and I want to mention is I already posted these slides in case any of you is interested in taking a look or already noticed mistakes that I'm sure there are many, and is kind enough to let me know. And just very quickly, let me show you. Yeah. Actually, the address is this. You just go to Mario Diaz, no dots there, .org, and you're going to get this page. And if you go to Natal Workshop, I guess it's a bit slow, internet here. Is every room as fast as the events? Wi-Fi? Well, it connected right away to EduRoam when I mean, it's in EduRoam now, and it worked. See, it actually, for some reason, I don't know why it's, well, but I think I have it cached here. So once you get into the Natal Workshop in that link, you're going to see this webpage, and the slides I'm using are listed there. So mariodiaz.org. And I'm going to be posting the slides as I'm going through in that website, in case you are interested in looking. From what so many of you don't really need this, but. And so I thought interested in going over this idea that Einstein developed of the gravitational redshift, because it's quite interesting in understanding the genesis of Einstein thought. So let's consider two coordinate systems, S and sigma. So this is S, and this is sigma. The two, at one particular time, have velocity 0. So essentially, they're totally aligned and static one respect to the other. Eventually, somehow, we're going to give it an acceleration. That's going to be gamma, uniform acceleration. And so we synchronize clocks at both reference systems. So we're going to use tau as the time in sigma and t in the other one. And same time, they're going to be both 0. And now, sigma is going to start moving with constant acceleration. But we're going to introduce a third system of reference, S prime, which relative to S moves with uniform velocity in the x direction. And we're going to take that uniform velocity to be proportional to this acceleration of this one. Remember, the only accelerated one is sigma. And an S prime is an inertial system of reference with respect to S moving velocity v. And at a given time, we can relate the coordinates x prime, y prime, and z prime with sigma. And v is gamma t. And then we're going to go one step further and synchronize all that time, at that time, all clocks in S prime with those in Z. So this one with this one. And now, if we consider an interval so small, space interval, between S prime and sigma, we can neglect effects of order delta squared. And that means that we still can use the time of the clocks in S prime to describe the rates of the sigma clocks, because the difference is only delta squared. And then we're going to use what we learned from special relativity, because we are considering small light paths. And S and S prime are inertial frames, and the changes in sigma are very small yet. So we can identify the measurements in S prime with those in sigma, except for higher order effects. And now, how do the clocks into the two different space points run relative to each other? We already said t equal tau equals 0. The two clocks were synchronous with each other. Remain for such interval of time that way, but S prime is not synchronous to them because of the Lorentz transformations. So then they do not remain synchronous to each other if the difference is not constant. And so we're going to see that define the idea of simultaneous events 1 and 2 in sigma using these formulas, where V is gamma t or gamma tau. But now 1 is going to correspond to the origin of sigma, and 2 to a point where the clock is reading sigma now at different time. And we make one last approximation. The time tau between S prime and sigma coincidence is taken such that we neglect effects of order tau squared. And then x2 minus x1 is x prime 2 minus x prime 1, which is theta. And t1 is tau, and t2 is sigma. So the previous equation then is going to become this. And of course, B is gamma tau. But if there is a time difference that depends on the acceleration, and we can see here, see T1, sigma, and tau are not equal. The difference is given by this factor, which is proportional to the acceleration. But times are the inverse frequency. That means the frequencies are different. So one experiments because of the acceleration here, a redshift. From this, Einstein said, there are clocks which are available at different locations with distinct gravitational potential. These are the generators of spectral lines. It follows that light coming from the solar surface has a longer wavelength than the light generated from the same material on Earth. This is before formulating the general theory. And of course, there were some ideas about what happened with light in terms of the particle view of light, but this is from the 18th century. So eventually, the Pound-Recca experiment measured that gravitational redshift with great accuracy, and many introductory books, textbooks on general relativity, you can see how the Pound-Recca experiment was made, and this is the shifting in the spectral lines is proportional to the uniform field, and of course to the height from where you're measuring the two values. So let me go now quickly into the principle of equivalence. And the first one is, the first discussion is, are inertial mass and gravitational mass the same or not? Well, historically, we know Galileo's famous thought experiment, and now trying to search for the meaning of this mass, we can compare Newton's famous gravitational wave formula with Coulomb's formula, for example, for the same particle. But now, in the Coulomb's formula, the quantity that we're going to use is related to another property of matter that obviously had nothing to do with inertial mass. So Galileo's experiment showed that the inertia and the gravitational are pretty much the same. And it seems that it's something that to gravity, and it's by the inertial mass. So the first formulation of the equivalence principle is, well, we already made that the previous discussion about the redshift, and Einstein said one can speak as little of the absolute acceleration of the reference frame as one can of the absolute velocity in the ordinary special relativity theory. And from this, according to the gravitational field, is self-evident. With gravity, we cannot attempt to describe the trajectory followed by particles and affected by this action. We cannot define an inertial frame at rest on Earth. Not even a photon could help to characterize it. All will be affected. But there is a frame where all particles keep uniform velocity. This is a frame in fall under the action of gravity itself. So the idea now is to take this first principle of special relativity, that there was this inertial system of reference on which all the laws of physics were the same, to a different now, an accelerated system of reference, the one that was in free fall in the gravitational field, and the laws of physics will be the same in those systems now. So this is a way of extending the special theory to the general theory, extending accelerated frames of reference. Now, why extending the inertial system of reference to the free fall system of reference needs a new geometry or needs geometry formulated? So there are inconsistencies, and well, it's beyond these short lessons to talk about this, but there is particularly one. I forgot now how it was called. It's the name of a famous physicist, but I forgot his name now. But think about this experiment. You have a disk. The disk is spinning. Now, if you apply Lorentz transformation to the disk, and you look at the disk as it is spinning, then you're going to see, applying Lorentz transformations, that the length of the circumferences cannot be 2 pi times the radius. Because you're not going to apply Lorentz transformation to the radius because it's orthogonal to the direction in which you're moving, looking at this spinning disk. But you have to apply it to the circumference of the spinning disk. So, but if the circumference, yeah. No, it wasn't Gamow. This is a Dutch physicist, and it has a name, actually, the experiment, but I forgot. I promise I'll look it up and bring it tomorrow. And there was a lot of debate about this, but this, what I like about this experiment is showing that even clearly in special relativity, you can now think that all geometrical concepts still hold. And now, let's look at this particular simple situation. So we have a rocket with an acceleration that is equal to the acceleration of gravity. So this is well far from Earth, isolated, and we have someone performing an experiment and looking at two freely falling particles in this accelerated frame of reference that has acceleration g in this direction. Of course, we know that this is going to be different from this other one in which there is no acceleration in the rocket, but we have now g. So the two objects are going to be free falling, and the observer is going to notice this. But there's no difference between both. But look at this now. If we have a lift standing on Earth, then we're going to see that the objects fall on converging paths, because obviously they're attracted, like if all the mass of the Earth was concentrated at the center of it. Now, one step further, if we drop the lift down the shaft, and this is the free system of reference to which Einstein is generalizing the theory, then we're going to see, as we free fall, that the particles are getting closer together. We have a way of distinguishing the presence of a gravitational field. This idea is extremely important. So, if we call this path the path that freely falling objects follow under gravitational field geodesics, that's the way I call it, how this path diverge or converge, so how they deviate from being parallel, is what indicates the presence of a gravitational field. This is an extremely important idea again, because when you combine all these ideas, you need a geometrical formulation in which incorporate all systems that could be in free fall, and you should be able to transform it from one to the other, from one to the other, to the other, to the other, without, regardless of the coordinate system of reference you're using. So Einstein took many years to realize that in order to do that, he needed to use he developed, and that's what he used. So let me talk a little bit about differential geometry. I'm going to be very quickly going now, and that honestly, I don't think you can really do. But at least, hopefully, I can make clear the jargon that I'm going to be using later, the words and everything, and those concepts are going to make sense, although it will require some more careful look. Differential geometry, an important concept is the concept of curves, which are mapping, going from a piece to a particular path in a plane. The number that we use is called a parameter, and the parameter lays essentially labeled points along the curve. On the relationship between the two parameters along the curve. Now, the thing is going to remain the same in spite of the transformation, because what we're trying to describe is a particular curve, a particular path on a plane. So, for example, if we have now a scalar field that is acting plane, and we want to see how it changes along the curve, what we can do is take this derivative, and it's going to tell us how that scalar field is changing along the curve. But a very important concept, and that's the reason why I'm introducing all this, is the sort of modern, maybe not so modern now, view of a vector that essentially is a geometrical object that transforms with certain properties and is tangent to a given curve. We're going to see that the transformation properties of vectors and another quantities that are called forms that are sort of related to vectors are at the foundations of differential geometry. And those transformations are crucial because we're going to need it for a theory of gravity that makes an invariant and covariant at the same time description of the laws of physics in all possible system of reference. So this to the curve here, and naturally a curve defines the vector field, or it's going to define the vector field. An interesting to talk about vectors, and these are the quantities that are duals of vectors that are called forms. See what happens with polar coordinates. This relationship between, this essentially is in a Cartesian unit vector in the x direction, Cartesian unit vector in the y direction. This is now a radial vector in radial coordinates related to the Cartesian base. This is the angular unit vector, and this is how it's related to this Cartesian base. And now, of course, we can define these quantities that I call one forms, and they have this tilde to make it different from the vectors. And they transform in this particular way. And they transform in this particular way. So notice that these quantities are different from these ones, but are what I call dual with the other one. And of course, that particular basis does not have length unit because we're introducing the cosines and the radial. But now, so there's going to be an important quantity that we're going to exploit it a lot that is called the metric. And in polar coordinates can be written this way in the Cartesian basis. Now, when we transform to the polar coordinates, the metric is going to be written like this, because all we use as a definition for the metric is that it's the scalar product of the unit vectors of the base. The Cartesian base gives 1, but now it's going to give, not the Cartesian, the radial, the polar base is going to give me this quantity. So the metric is going to have these values in the Cartesian coordinates, these values in the radial coordinates, and displacement is essentially differential of length squared, which we write this way, and it's going to give me this quantity. The inverse is going to be given by this. And notice now, and this is where hopefully by introducing this quantity this way, for those of you that haven't been used to this notation, so notice is there are indices at the bottom, so subscripts, and there are indices that are superscripts, so they're at the top. And they clearly show a difference between one matrix and the other one. One is the inverse of the other one. So if we have a scalar field, and this is the gradient, which write it this way, because a gradient is not a vector, but it's a covariant vector, one form. And this has the components that can be written with this, and they transform this particular way. If we're looking at the indices being below, they're going to transform with the inverse of that matrix. So that's going to be the difference when we look at indices up and indices down. So the polar basis is now constant, the Cartesian basis vectors, and we can take derivatives this way, and we get this quantity. Similarly, we can take derivatives of the other vector, and we're going to get this. So, derivatives of general vectors. Simple example so the notation becomes clear who have never seen it. It has also components in the relation through the metric. And we write it this way. And in component notation, it's going to be written like this. So a generalized form, then for the derivative of a vector to the coordinates can be given by this. Notice that we have an extra term in doing these calculations. So the idea is to write this extra term in terms of the same basis. In order to do that, we're going to say that it's going to be a linear combination of the elements of the original basis. The terms that are going to give us, notice that alpha goes with alpha, beta goes with beta, and then mu and mu indicates a sum. So in this case, where we're in a two-dimensional system, it's going to be 1 and 2. So this is defined in a quantity that are called the Christoffel symbols, and alpha gives the basic vector be differentiated, beta gives the coordinate respect to which it is being differentiated, and mu is just denotes the component that we have in the array. So doing all the calculations, we can calculate these Christoffel symbols in the probably simplest case that you simple Cartesian metric when you move it to polar coordinates. So now, essentially, this is what we wrote. Notice that the derivative now of the vector can be expressed in terms of these two quantities thanks to the help of this quantity that encodes the transformation of coordinates that we use. This is a crucial concept. So if we relabel the factor, finally we can write it in terms just of the vector of the basis. So this derivative now, when we calculate it in these systems, we have sort of more general derivative than the one that we're used to in standard calculus. This is called the covariant derivative. It's a derivative that you can take even when you're looking, for example, doing this calculation on the surface of a sphere. The traditional derivative, you can only calculate it, you can only do it when you're working on flat space. Now, if the space is not flat, it's going to encode information here, and then that's the way we calculate. Of course, if we have a flat space, the Cartesian metric for flat space is going to give me all these terms 0, and then the covariant derivative is the traditional derivative. So this is a tensor, and it's very important because what we use in general relativity are tensors, so quantities transformed with these laws. And so a scalar does not depend on basis vectors, so the covariant derivative is just a simple one. So this goes on only for vectors and higher order quantities. So what is the meaning of covariant differentiation? Well, I'm not going to do the calculation here. The idea is, because of the lack of being on a flat space, you're in a curved space, then if you try to move something parallel to itself, it won't remain parallel to itself. Eventually, it's going to be a displacement. The covariant derivative measures that displacement to the curved surfaces on which you're doing the calculations. And so this continues. So for those of you who want to really look into this, you can read the slides. So I don't want to spend too much time on this. And it shows now how you actually measure in exactly this difference through the Christoffel symbols that encode the curvature in the formula. So covariant derivative then can be defined in these terms. And you know, I look now at smaller transformations to do a standard definition. Now, going back to the idea of a metric. So the metric, so let's think about this. We're going to require tensorial equations to transform covariant index into contravariant one using the metric. We can calculate the Christoffel symbols from the metric. And the fact that the metric is a 0, 2 tensor. 0, 2 means that the two indices are underneath. If I put the 2 up, then it's going to be 2, 0. And so the properties they're going to have for the Christoffel symbols, they're going to be symmetric in these two indices, and that the covariant derivative of the metric is 0. Actually, if you want to do some exercises for these lessons, you can try to prove that just using the definition, and it's going to come naturally. And of course, we are assuming that the theory of torsion, which is the difference. So if the connection, because of the metric you're using, wasn't symmetric, then you have in the space what is called torsion, but I'm not going to go into that. Although there are theories of conditions that are not necessarily torsion-free. So, so the connection is going to be metric compatible if the covariant derivative of the metric with respect to that connection is everywhere 0. And these are a few properties that you can calculate for covariant derivatives. And I'm going to go through them. And what I want to go is into this formula. If you have then the quantity and the consideration. And let me talking about mappings only for a second, because I want to introduce another concept that is very important. So if I have a space M and a space N, a map is going to be a function that takes me from the space M to the space N and associate a unique element in N to each element for which I do in this on M. So the map is going to give a unique F, taking me from N to N. Not necessarily it's going to be unique X for every F of X, of course. And so now let me go into the definition of manifold. So a manifold is a set of points which have an open neighborhood that has a continuous one-to-one map, that's the reason why the definition of mapping, onto an open set of the real numbers for some n. So a manifold of dimension n, let's say 3, it's going to have a set of points that I can map to R3, so that the real numbers in 3 dimensions. A priori, we don't require a metric on a manifold, but everything that we're going to do for general relativity can happen on a manifold. So and of course, we can put coordinates to label the different mappings that we can do. And so here is an example, S2. So S2 can be mapped to the plane. It's going to have problems, as you probably all know, for some particular points at the poles. And so we can have a different mapping. And this is called stereographic mapping that also goes into real numbers, but now with some particular assignments. So notice that I have the real just tangent to the south pole in order to do this particular different definition. And well, there are examples. Set of rotations of rigid object in 3 dimensions is a manifold. And Lorentz transformation also can be given the structure of the manifold. I'm not going to go too much into this. So how about now differentiable manifolds? So we expect our manifolds not only to be continuous, but to have maps that can be differentiated with derivatives, which will also be well defined, maybe exception of a few points. The sphere, it's always continuous and differentiable. A cone everywhere except at the vertex. And differentiability to have vectors on one forms, and then with this we construct all type of tensors. So once we define a metric on the manifold, we will have a correspondence between forms and vectors. And so, a review of tensors now. This was a true crash course on tensor. Tensor field defines tensor at every point. Vectors on one form, so linear operators on each other producing real numbers. Tensors are also linear operators on one form, some vector producing real numbers and tensor operations. Multiplication by scalar produces another tensor of the same kind. Addition of tensor components of the same type, otherwise we can talk about that, produces another tensor of the same type. A multiplication of tensor of different types, and that's going to be a different new tensor with some of the types. It's called the outer product of two tensors. So, for example, covariant differentiation of tensor type Mn gives a tensor now that has one extra covariant index. Contraction of pair indices, it's going to get down on both indices. So the type is going to be reduced into one covariant, one contravariant. Any tensorial equation valid in one base is true in any other one. And that's the reason we're using tensors, because we want equations that remain invariant. So now let's go to Riemannian manifolds. And so in differential geometry, tangent space can be defined at every point of the differential manifold. Simple example, a sphere. And now let's look at a point and a plane that is tangent to the sphere at that point. And is a real vector space, can be pictured instantly, containing possible tangential direction, could be defined at the point. And so this is quite simple. Now, Riemannian manifold is a real differentiable manifold in which each tangent space is equipped with an inner product given by the metric, a Riemannian metric, in a manner which changes smoothly from point to point. The metric is a positive definite symmetric tensor for a Riemannian manifold. The metric is important because with the metric we calculate angles, lengths of curves, areas of volumes, curvature, gradients of functions, and divergence of vector fields. So a Riemannian manifold is a differential manifold in which a tangent space at each point is a finite dimensional Euclidean space. In all truth, what we're going to use is a pseudo Riemannian manifold because, remember Minkowski, the time has a minus sign associated with it. Actually, you can do an entirely equivalent construction using the plus for the time, a minus, minus, minus for the components of the metric for the space-like coordinate. So this metric is going to let us have is a tangent space at any point. And what is interesting is with this type of metric, we can have vectors now that have larger than 0, 0, or less than 0 length. The metric is going to be symmetric. So how far am I? Actually, I'm doing pretty good with time. Well, so let me talk a little bit about this idea of local flatness. Any point of the manifold, we have a tangent space associated naturally to it. Any point on the manifold. The idea is that with the metric, we have a unique way to associate a one form with the vector, and vice versa. So with each vector, we can associate a one form. And actually, we don't want our tangent space to be Euclidean. That's the reason we pick up a Riemannian manifold that has this signature. We want, in the end, this tangent space to be Minkowskian in nature. In other words, we're going to be able to diagonalize the metric, and eventually you're going to have eigenvalues -1, 1, and 1. So be like minus dt squared plus dx squared plus dy squared plus dz squared. The sum of the diagonal elements is what is called the signature. So as you can see, it's just +2. Another point is that in order to have coordinate bases, we need matrices that can be turned into a Minkowski metric. So we're going to need this type of transformations here. This is probably not all that important. The local flatness theorem, let me point, obviously it's beyond the scope of this, trying to prove this. And I ran out of my, do you have another pointer? Yeah. Or 2 batteries. Yeah, at least I'm going to be able to, yeah. I can still shift slide, but I need a pointer to. So this is very, very, very important because we're going to be using this. At any point in a pseudo-Riemannian manifold, we're always going to be able to find a coordinate system at the origin where the metric can be written like the Minkowski metric plus correction of second order. We're going to be using this when we go into discussion of gravitational waves. fantastic. Yeah, full battery. Excellent. Thank you so much. So, an equivalent way of saying this is that the metric can be written in that tangent space as a Minkowski metric. The derivatives, of course, also going to be able to, they're going to be just 0 because it's a Minkowski metric. Minus 1, 1, 1. Take the derivative, it's going to be 0, 0, 0. But we can have changes of second order because it's only true in the neighborhood of the point where we're making the calculations. So in order to calculate length, we're going to be able to use a metric. And so this is length along a curve. We're going to calculate it using the metric, see? This quantity is actually called Diaz squared. So integrating Diaz squared square root, which is Diaz, gives the length of a curve. And we can do it between two values of the parameter along the curve. And we can also calculate the length of vectors with a metric. And the most important thing, or very important thing, is we calculate volumes. So if we use a standard definition of volume, it's going to be related with this quantity to the prime system to which we do transformations through the Jacobian of the transformation from one coordinate system to the other. So the determinant of Minkowski metric would take us to the following result, which essentially the determinant of the metric is crucial to give us the proper volume element. So for example, you can see this, and the traditional example is how you calculate a volume, but this you do it in calculus 1 or calculus 2 very early in your career. But so that's an example that shows that's all I'm actually saying. Now, let me, look, I think I explained enough of covariant differentiation. We talk a little bit about the concept of curvature. So one is the extrinsic curvature, and that embedded in another space. And is related to the radius of curvature of circles that are in the embedded space. So the extrinsic curvature of a circle is equal to the inverse of its radius. Now, intrinsic curvature is defined at each point in a Riemannian manifold. An intrinsic definition of the Gaussian curvature at the point P could be, for example, this. Look at a point P, and now let's think that you have a short thread, and you have an ant on another poor being that is willing to take the end of this thread and go around completing, fully stretched, completing a circle of length C of R, where R is the length of a thread. And it's just one circle around P. So we know the result if the surface is flat is 2 pi R. But now on curved surfaces, we're going to get a different result. And what is called the Gaussian curvature at the point can be computed by this particular formula. 2 pi R minus the length of the circle times 3 divided by R squared, and the limit of R goes to 0. And if you apply this formula to circle, we get it 0, meaning that the intrinsic curvature of a cylinder is 0. Now, a clear example of intrinsic non-zero curvature is the failure of Euclid's fifth postulate. So if we took a look at two vectors that are parallel to each other at the equator, let's think now that we want to try to move one along this particular path that goes through the equator, up through a meridian to the north and come down through another meridian to the original point at the equator. So what we're going to get is this. If you were to do this consistently, moving it parallel to itself, you can see that it doesn't come back to be the same vector. So it's been a rotation. And this is important because crucial idea here, we wanted to do a parallel transport of the vector itself. So this idea of parallel transport, we can come back to the idea of covariant derivative. So if the covariant derivative of a vector taken along the direction defined by the same vector happens to be 0, we're transporting the vector parallel to itself. And so it can be written in these terms, and if we put it now in a notation where we can actually make the calculation using the components, essentially it's going to be the regular derivative along the curve plus these terms. Notice that these terms being non-zero is the one that make this calculation different from the regular in flat space. So if we let the S be the parameter along the curve, then we can write the vector as in terms of the variation along the curve. And essentially what we're going to have is an equation that's called the geodesic equation. And we can, of course, use another parameter that's linear related to the original one, and we still have an equivalent equation. So a geodesic is a curve of extremal length between 2 points. It's the generalization of the fact that the extremal or minimum length between 2 points in Euclidean space is given by a straight line. Now we generalize this concept to curved spaces in general. So it can be shown, but we're not going to go into details into this. The proper distance along geodesic is an affine parameter itself, and this is the way geodesics are typically calculated. Now, this idea of geodesic is crucial because in curved space, what the principle of equivalence tells us is that freely falling particles are going to move along the geodesics of that geometry. So if we wanted to parallel transport a vector defined at one point A through a closed loop A, B, C, D, then I go, a bit quickly through these slides. If someone is interested, can look them up. And I'm doing all the calculations of parallel transport and doing, integrations now along the particular lengths to get the vector, how is the vector is changing. And remember, I'm calculating the changes of the vector along the geodesics, but I want to see the vectors themselves, how they change. And the terms eventually don't cancel. Keep going through all the loops and keep doing this. And I'm going to spend too much time on this. I want to show you the end result. And the end result is this. The change in the vector is going to be given by the changes B are given here. So this is A where I start. So this is one of the lines. And now I came, and this other one is A plus delta A. So there's this change between these 2 points, and between these other 2 points is B plus delta B. So a change in this quantity and this particular construction that is made with derivatives of the Christoffel symbols, the connection coefficients, times the original vector. So this is how much the vector changed. Between brackets, this quantity constructed with the Christoffel symbols is what's called the curvature tensor. And notice there is 1 index up, 3 indices down. So this is how we write the Riemann tensor. And here it is. Now, the Riemann tensor measures how much a vector transported parallel to itself around a closed loop in a given manifold has departed from being parallel. From its definition, we see that if the manifold is flat, the vector remains parallel to itself after the transport. And so we can look at another way of calculating this, which is calculating the commutator's covariant derivatives. And I'm going to do this. I'm going to split it. The result is going to be in the end the same. And the way we define the Riemann tensor is a 1-3 type, in the sense 1 index up, 3 down. And essentially another way of saying measuring how much a vector doesn't transport parallel to itself, fails to be transported parallel to itself along a loop in that geometry, which is defined by the Riemann tensor, and is how the covariant derivatives do not commute between them along this path. Now, the interesting thing is that this Riemann tensor now can be put in terms of the metric. And we can do it in a locally inertial frame. And remembering the definition of the Christoffel symbols, then what we can do is put the Riemann tensor in terms of the metric. So if we're given the metric, we are given the manifold. Sometimes it's going to be hard to see behind what the actual structure is. That's the reason why invariants that can be constructed, and those can be constructed through the Riemann tensor. But the Riemann tensor, through the metric and its derivatives, notice that goes up to second order derivatives of the metric. It's going to characterize the geometry of a manifold. We can lower the indices. There's some other properties. So one interesting thing is that if the Riemann tensor has all the components, when I say A, B, C, D, it's no index, it means for all A's, B's, and C's, and D's, that means this quantity there has 256 components, yes? Component is 0. We have a flat manifold. So the last concept, if you remember when I tried to somehow follow the history of Einstein thought, I look at an observer in free fall, in system of reference, in free fall, looking at two particles that were also in free fall. And I said, the way that this person can distinguish is looking at how the particles are changing along their free fall. So let's look at two geodesic curves, which are the curves followed by particles in free fall. And of course, they're going to be a solution of the geodesic equation. We use lambda as the theme parameter, v and v prime as respective tangent vectors to each of them. And so, you know, this is one curve, and it's going to have v prime. This is v. So these are the two curves. And I'm defining along the geodesics these particular vectors that are connecting the two geodesics. And define theta is a vector that connects both, and for a given value on one to the similar value lambda on the other one, for example, the proper time along each geodesic. And like, for example, these are two parabolas. They're two geodesics. And actually, they constructed using this formula. So if we want to investigate how much one departs from the other, let's look at the two surface spanned by what's called a congruence of time-like geodesics. So this is going to be a family of geodesics, such that exactly one of the curves go through every point of S. Parametric equation is going to be given by this. This is one vector. This is a connecting vector. So V is a tangent vector to line geodesic at each point, and theta is connecting vector to neighboring curves in the congruence. If we calculate the commutator, we're going to get this formula. And replacing by the covariant derivative. So to remember, V is the vector, theta is the connecting vector. And I'm going to introduce one more concept now, which is the concept of lead derivative. So this is taking the covariant derivative along the v vector of the covariant derivative of the connecting vector, and now the covariant derivative of the covariant derivative of the vector itself with respect to the connecting one. So this suggests that we can have this definition using u and v, where you can think that u is the zeta, is the different vector, and this is exactly the terms interchange. So this will be, notice that alpha is up, alpha is up, alpha is up, and there's a sum here, and there's a sum here. So this particular calculation is called a Lie derivative. That could be very useful because we don't use the metric in doing this. So, and we can calculate it this way, and the bracket is called the Lie derivative of y along x. So in this case, that's the reason why I wanted to define it, because it's the Lie derivative of v with respect to the connecting vector. And the Lie derivative is defined for tensors in general. And one interesting property is the Lie derivative of a given tensor type does not change it at all. It's the same. And so now, after doing the calculation, what I see, and this is the most important result if you couldn't follow what I said before, is that these two consequent covariant derivatives of the vector along the geodesic are going to be related to the vectors and the connecting vectors of the geodesic by this quantity. This quantity is the Riemann tensor. So geodesics in a flat space-time are going to remain parallel. The separation is going to remain constant. But geodesics in the curved manifold do not in general. And the Riemann tensor is a measure of how much they don't. And we go back now to this original motivation. We throw the two particles, the particles are getting closer together, and this is how we know that there is a gravitational field. So the central idea leading to the theory of relativity that makes geometry necessary, actually, yeah, I'm planning to do one slide more, I think, and this one, and this is pretty much the end. So the path followed by test particles is going to indicate the curvature of the geometry. If we call geodesic this path, how the path diverge or converge is what indicates the presence of a gravitational field. With these quantities now, the Riemann tensor, we can construct, well, these are properties of the Riemann tensor. I'm not interested in covering those. But we can construct this quantity that is important. Look, this is a contraction of the Riemann tensor. This index means I sum up these terms. So I get now a tensor that is smaller. It's only 0, 2. This is 1, 3. This is 0, 2. And this one is called the Ricci tensor. With the Ricci tensor, using the metric, for example, I can contract it, and essentially add up. It's like adding, if I had diagonalized it, would be adding the terms of the diagonal. It's be a Ricci scalar. And I'm going to go through the Bianchi identities, but the main idea, and with this actually I'm going to finish, is with the Ricci tensor, we can construct a tensor. It's called the Einstein tensor that encodes the geometry. And notice that it's written in terms of the Ricci tensor, the metric, and the Ricci scalar. This is the Einstein tensor. In particular, if we make this equal to 0, these are vacuum Einstein field equations. I'm going to end here because I think after this marathonic general relativity crash course, I can start at the more leisure pace into the weak field limit and how we use Einstein's equation to find that predict the existence of gravitational waves. Sorry to those of you who found this too much, but I didn't know other way of doing it. Yeah, that's the end.